Hi, everyone, and welcome to online lecture 28. This will be the exam 3 review. Again, this is the exam 3 review. So we start off with this old family circus cartoon. I wish they didn't turn on that seatbelt sign so much. Every time they do, it gets bumpy. So, of course, this is an error with correlation and causation, and they've got the idea backwards, right? So, okay. And then everybody who went to the moon has eaten chicken. Good grief, chicken makes you go to the moon. Something quite similar, although this time I might argue this is more of a regression problem, but either way, whichever way you want to think of it is fine. Okay, so now let's get right into it with the exam examples. The following 5 questions are examples of the sort of questions that could be asked on the exam. And at least one of these 5 questions will appear as is on the exam. The only difference might be that the answer choices will be in a different order. Okay. Dr. Snoopy A. Beagle has completed a research study and creates a scatter plot depicted below. Which test should he use to analyze his data? So think about it, pause if you like. And now I will tell you that the answer is D, none of the above. Now, the reason it's D, none of the above, is first of all, we're looking for some kind of linear relationship here. We're using a scatter plot. The only one it could have really been was Pearson correlation coefficient, but this isn't a line, is it? It's more of a curve. And remember, neither Pearson nor regression nor any tool we have in our toolbox can be used to analyze this kind of scatter plot. Okay, when you've got a curve, we've got nothing to use. All right. 12 high school juniors planning to attend college were randomly assigned to view one of 3 different videos about a particular college. Each video differing according to what aspect of college life was emphasized: athletics, social life, or scholarship. After viewing the assigned video, each student completed a measure about their desire to attend this particular college. A recruiter at this college is interested in whether there will be any difference across the 3 videos. Assume alpha is 0.05. Using the SPSS output below, determine which groups are different from each other. Note, there are 5 answer choices below. Okay, so we're going to use SPSS output to figure out which groups, and I guess it has to be something because there's no, none of the above choice. So it's got to be one of these choices here. Okay, so let's look at the output. Here's the output, and good, this is significant. Our ANOVA is significant, meaning that we're going to have at least one difference here, maybe 2, maybe 3, but at least one difference. Okay. So now let's figure out where the difference is. Okay. So first we compare athletics and social life. We come across and we see a sig value of 0.006, and we ask ourselves, is this less than our alpha of 0.05? And the answer is yes, 0.006 is. So there is a difference between athletics and social life. Wonderful. Now let's look at athletics and scholarship. Go across to the sig value, and it's 0.017. Is this one less than 0.05? Well, yes, again, it is. 0.017 is less than 0.05. So we also have a difference between athletics and scholarship. So you might want to take a note of this. Athletics and social life is different. Athletics and scholarship is different. We have one more to look at, and that's social life and scholarship. That's row 4. Row 4, 0.787. Is that less than 0.05? And the answer is no, it's not less than 0.05. So that one's not different. So there is a difference between athletics and social life and athletics and scholarship, but not between social life and scholarship. So let's go back to the answers. Okay, I see athletics and social life. I see athletics and scholarship. So both of those is what I'm looking for. And I see that E says both A and C. So that will be my answer. E, both A and C, athletics and social life, athletics and scholarship. Let's move on to the next one. Lucy believes that higher levels of job satisfaction are associated with lower levels of absenteeism in the workplace. She obtains 32 participants to whom she administers measures of job satisfaction and absenteeism. Assume alpha is 0.05. She completes the analysis and her calculations reveal that R equals 0.726 and P equals 0.02. Which conclusion should Lucy reach? So I'll give you a chance to pause for a moment while I read. I'll go ahead and read aloud the different choices. Reject the null hypothesis, the result is in the predicted direction. Reject the null hypothesis, the result is not in the predicted direction. Do not reject the null hypothesis, the result is in the predicted direction. Do not reject the null hypothesis, the result is not in the predicted direction. So pause here if you would like. Now I'll tell you the answer. Okay, so we predicted, or Lucy predicted, I should say, that higher levels of job satisfaction go with lower levels of absenteeism. In other words, she is predicting a negative relationship, a negative correlation. Now, when we look at this correlation, it's actually positive. It's 0.726. It's not negative 0.726, it's just 0.726. So that's a problem because we predicted it was going to be negative and it was positive. So our answer is going to be D. Do not reject the null because the result is not in the predicted direction. So do not reject the null hypothesis. The result is not in the predicted direction. Remember, for anything except ANOVA, ANOVA, we only have two-tail tests, but for all other tests, we can have one-tail or two-tail. And when it's one-tail like this, we've got to match the direction that we claim. In this case, we didn't, so we don't get to reject the null. Okay. Now let's look at this one. 48 participants were randomly assigned to do math tasks under one of three conditions. 16 while listening to soft, gentle music, 16 while listening to loud, intense music, and 16 while in silence. You wish to know if there is a difference in math scores across the different music conditions. You are provided with the following information. SSW equals 1156.5, MSW equals 25.7, F equals 3.2, and P equals 0.03. Assume alpha is 0.01. Which of the following statements is true? And our choices are: reject the null hypothesis since the results suggest that all of the groups are different from each other. Reject the null hypothesis since the results suggest that there is at least one difference between the groups. Do not reject the null hypothesis since the results suggest that none of the groups are different from each other. And do not reject the null hypothesis since the results suggest that at least one of the groups is not different from the other groups. Okay, so there's two things being assessed here, right? And again, I'll invite you to pause if you want to take this on your own and think about it. Okay, so now I'll tell you, there's two things being assessed here, right? So one is, when do we reject a null in ANOVA? You reject a null when there is at least one difference. That's all you need. You don't need everything to be different from everything else. You just need one difference to reject. Okay, how do we know if there's at least one difference? The same way we always do. Our P has to be less than our alpha. So we ask ourselves, is 0.03 less than 0.01? Well, no. It's not. 0.03 is not less than 0.01. In fact, it's greater than 0.01. So we do not get to reject the null hypothesis. Why? Because the results suggest that none of the groups are different from each other. Okay, so when you look at this problem, you should be able to immediately eliminate A and D, because those are just not true of ANOVA. We don't need all of the groups different from each other to reject. And we're not going to not reject if just because one isn't different. We reject if there's at least one difference. We do not reject if there's no differences. In this case, because P was not less than alpha, there are no differences. Okay. And so you might be wondering, in this case, would I even look at a Tukey? The answer is you don't need to, right? Notice I didn't give you one. I didn't give you that post hoc test because you didn't need it, because you already know there's no differences. Okay. Patty wishes to determine if swimming ability is associated with agreeableness. She obtained 60 volunteers who obtained a medal in swimming at the 2016 Olympics. Each participant is given an assessment of swimming ability as well as a questionnaire to measure agreeableness. Marcy, a colleague of Patty, determines that Patty has a problem with her study. What is the problematic issue with this study? And the choices are restricted range, outliers, extrapolation, and none of the above. So I'll invite you once more to take a pause, think about it. And now I will tell you that the answer is A, restricted range. This is a classic example of what we talked about with restricted range. She is trying to see if swimming ability is associated with agreeableness in the general population. Does she assess the general population? No. She assesses a very specific group of top swimmers, right? You got to obtain a medal in swimming at the 2016 Olympics. We can assume these are very, very good swimmers, right? So just because she might find a relationship here or doesn't find a relationship here doesn't mean anything. Doesn't mean anything about what she would find in the general population. That's an issue of restricted range. She restricted her range of who she was looking at, and that's a problem. Okay. So now, oops, excuse me. Those are the 5 questions. Okay. Now I'm just going to go through a couple of quick things I think might be helpful for you to look at before the exam. And the nice thing about this exam is we didn't do any hand calculations at all, really, right? I mean, we looked at R and R squared. You had to square R. You still have to divide p-values by 2, but nothing really major. And so my point is we didn't look at any tables. We didn't look at any manually calculated stuff. So we're going to skip that slide. And instead, we're going to jump right into how you interpret things in SPSS. So if the observed p-value or sig value is less than alpha, the result is statistically significant and we're likely to reject the null. If the observed p-value is not less than alpha, the result is not statistically significant and we do not reject the null. Now, remember, I've had this likely phrase before. Why do I have it there? Why don't I just say reject the null? Why do I say you're likely to reject the null? It has to do with one-tailed tests. Okay, so with ANOVA, you could get rid of the likely. You can just say reject the null. Because the ANOVA, we're only looking at two-tailed tests. So any kind of ANOVA, if the observed p is less than alpha, it's statistically significant and you reject the null. If it's a correlation or regression, then you got to look at if it's one-tailed, and if it's one-tailed, you got to look and see if it's in the correct direction. So the exception to the rule is if you have a one-tailed test and the results are in the opposite direction of what is stated in the alternative hypothesis, you do not reject the null. Again, if you have a one-tailed test, remember that's when you're predicting direction, and the results are in the opposite direction of what's stated in the alternative hypothesis, do not reject the null. And once again, I have an offering for you of symbols. Here's our sums of squares between, within, and total, all for ANOVA. Degrees of freedom between, within, and total, all for ANOVA. Mean of the squares between, within, and our F-test or ANOVA. So these are all for ANOVA. We don't have many symbols for correlation and regression. First one, Pearson correlation coefficient. Second one, coefficient of determination or percent of variance accounted for. Okay, so the first one is our Pearson correlation coefficient. The second, the R squared, is called our coefficient of determination, and it tells us the percent of variance accounted for. Our y hat is our predicted y on the regression line. Okay, so the top two are correlation, the next three are for regression, and our y hat is our predicted y value on the regression line. So what's plain old y? Just your point, right? Just the y for the point. What's plain old x? Just your x for the point. What's a? That's your intercept. That's your intercept. That's what y is when x is 0. And what's b? That's your slope. As x goes up by 1 unit, what happens to y? As x goes up by 1 unit, what happens to y? Okay. So that's all I have for you guys for today. That's your exam 3 review. We can answer, I'll be happy to answer any questions for you about this. And in the meantime, please take care, stay well, and I'll talk to you soon.